Good evening, Bearcats. This is 6.3 Vectors in the Plane. In the real world, when we deal with things such as force and velocity, we need more than a flat plane. They're three-dimensional. They have to do with direction and magnitude, which is the length of something, and they cannot be represented by a single real number. So we represent these by directed line segments, which are called vectors, and that's what we're going to discuss tonight. Directed line segments. There's some key vocabulary words that we need to talk about, and so I'm going to write those down. I would suggest you have those in your notes. Tomorrow when you come in, I am going to have you pick up a note sheet, and some of this will be in the note sheet, and there'll be some things for you to fill in, and you want to annotate your note sheet based on the notes you take tonight from the video. Okay, I've listed here some of the key vocabulary words that you're going to want to know, and some you are familiar with from our study of trigonometry. Some are you familiar with from your experience in algebra, and maybe some will be new for you. A directed line segment. Basically, a vector is a directed line segment. Notice I have the word directed underlined several times. In the past, when we used a distance or a formula or something, it didn't really matter. The little subscripts that we looked at were x sub 2 and x sub 1, and there was a particular way they were written in the formula. And it didn't always matter when you were looking for slope and distance and things like that, because we were only talking about a flat plane surface, and it just didn't make a difference. But now we're talking about a direction as well as a distance, and so it does make a very, very big difference on which are our initial points and which are our terminal points. In our study of trigonometry, we had the initial side of an angle and the terminal side of that angle of that rotation. The same thing happens here. You notice I have this vector, and I've made an arrow toward the initial point, and then down here I'll put a little point at the end of the arrow. That would be the terminal point. The initial point would have a set of ordered pairs x, y, and that would be your 1, subscript 1, and your terminal point would have your x and y value, and that would be subscript 2. So when we use the distance formula to find the magnitude, and there's a word that we haven't used a lot in math, I know you use it in science quite a bit, which is the length or the distance of that line segment. We'll use the distance formula that you're familiar with, but all of a sudden these little subscripts become very important. If you mix up your initial and terminal points, then the direction of your vector will be incorrect, and then of course the problem will be incorrect. So you may want to take a moment to pause and just write all of that down and make sure you have really good notes and annotate anything that you want. Let's take a look at this example. These are two vectors. This top vector we're going to label it vector V. Its initial point is point R, and its terminal point is point S. The second vector you see here, the one below it, is vector U, and its initial point we'll call P, and the terminal point we'll call Q. And you notice we have ordered pairs representing each of those points. All right, let's first find the magnitude, which now you're going to relate the word magnitude to distance or length. Let's first find the magnitude of PQ, which is the lower one. We would substitute into our distance formula, and we would have 3 minus, 3 minus 0 squared plus 2 minus 0 squared, and when we do that we'll end up with the square root of 13. Notice the 3 came first because this would be your subscript. This would be your x sub 2 and your y sub 2, and this is your x sub 1 and y sub 1, and therefore the order is very important now. If we find the magnitude of the other vector, which would be our s, let me put a little vector above these, sorry, then we will have also substitution into our distance formula. We'll have 4 minus 1 squared plus 4 minus 2 squared, and when we figure that out, we'll also have the square root of 13. So in other words, in this particular case, both of these vectors have the same magnitude, or the same length. Now, if I go through and calculated a slope, the first slope would be 2 minus 0 over 3 minus 0, which would be 2/3. And that would be vector U. For vector V, the slope would be 4 minus 2 over 4 minus 1, which again would be 2 over 3. So again, they have the same slope and the same magnitude. Because they have the same slope, then they are both traveling in the same direction. So we could say that vector PQ is equal to vector RS, or vector U is simply equal to vector V. But for two vectors to be equivalent, they have to have the same magnitude and the same direction, and those are two ways in which you would find that out. You definitely want to have that in your notes, and I would pause to write all that down and make sure you understand it. All right, let's talk next about the component form of a vector. If a vector is in standard form, just like if an angle is in standard position, then the initial point is at the origin. And the same was true in our unit circle if we started at the x-axis and rotated to the left. If both the initial and terminal points lie at the origin, if that happens, then the vector would be called the zero vector, or 0 would equal the vector form or component form 0, 0. The component form is listed here as V, which represents the word vector. Your vector is equal to vector V1, V sub 1, comma V sub 2. Please know that these are components of vector V. So V sub 1 and V sub 2 are components, are parts of the vector. Each one would have it's basically, this is like the x value of the ordered pair, so this is like x sub 2 minus x sub 1, and this is y sub 2 minus y sub 1. And that's how your component form is found. We're going to do, we don't use x and y's always, we use other letters, whichever the points are. I'm going to give you some examples here in a minute of component form. I'm going to let you pause and go ahead and write this down, and then we'll go on. Okay, we have some the format of this now for you about component form. We're going to continue our component form. Notice I wrote my little Go Bearcats over here with these little arrow brackets. Those little arrow brackets means that we're discussing or we're talking about it's the component form of a vector, and that's the notation for that. Like we've had soft brackets before, and we've had hard brackets before, and we've done with notation. These happen to be little arrow brackets that represent the notation for a component form of a vector. All right, let's say for a minute that our initial point P of a vector, and we'll just even draw this. Let's just draw a vector, and this is our initial point, and it has an ordered pair P sub 1 and P sub 2, which what you're going to think of more is like your x and your y value for that point or that ordered pair. Then we have the terminal point, which is Q, this was P, and the terminal point is represented by Q sub 1 and Q sub 2. Again, you're going to be thinking that as an xy ordered pair of your vector. So let's find the vector or the component form of this vector, the component form of this vector. All right, we would set this up, and we would do Q sub 1 minus P sub 1. And that would be your x value, or the V sub 1, that's going to equal our V sub 1. I think of it more like that's your x, and your x, you're subtracting your x values, sort of like in the distance formula, x sub 1 or x sub 2 minus x sub 1. All right, and then we're going to have Q sub 2 minus P sub 2, which is like your y values that you're subtracting. When we do that, this Q sub 1 minus P sub 1 becomes V sub 1, and Q sub 2 minus P sub 2 becomes V sub 2, and that's how that's derived, and that is equal to our vector. Okay, so our vector is equal to that. Now, next, let's talk about the magnitude of this vector. How would we do that? Notice that this part, if I substituted this as x sub 2, x sub 1, y sub 2, y sub 1, this would look very familiar to you, and that's what these are. This is like your x, y, 1, 1, x 2, y 2. This is a big part of your distance formula. So when we find the magnitude, which we have to find quite often, you're going to have the magnitude of the vector denoted by these double lines. there's double lines. That is going to be equal to, we've already written down the traditional distance formula, but now we're going to write it with our q's and our p's. So q sub 1 minus p sub 1, and then we're going to add to that q sub 2 minus p sub 2. Now, here's the deal. When we do this, we've already, when you find the component form of the vector, then this, if you have component form, if you don't have a component form, you just started with ordered pairs, you're going to have to do all of this. But if you've already got the component form, then this is this part right here, and this is this right here. So the magnitude of your vector then becomes the square root of v sub 1 plus v sub 2, which is the vector. If the magnitude of the vector, okay, so just making sure you understand that. So if you've already got component form, part of your distance formula and part of finding the magnitude has already been done for you. The little bit, actually, the more tedious part. The one thing else I want to note is if your vector has a magnitude of 1, it is called a unit vector, which makes perfect sense with our unit circle. That was when our radius was a length of 1. So we are just following through and tying some things into some previous learning. Okay, let's do some examples of a component form. All right, here we have two ordered pairs, point P and point Q. We're going to say that this is the initial point, and Q is your terminal point. All right, so first let's find the component form of the vector. So we're going to find V, our vector, and to find that, we're going to do our little arrow brackets, and we're going to have, remember, this is like your P1 and 2, and this is your Q1 and 2, so we're going to have negative 1. Always start with your terminal point. So we're going to have negative 1 minus 4, and we're going to have 5 minus negative 7, which will become positive. So all of a sudden, our vector is going to become negative 1 and negative 4 is negative 5, 5 and 7 is 12. So the component form of our vector is negative 5, 12. Now we want to find the magnitude of this vector. Remember I said if it's in component form, you've already done your basic from your original distance form, you've already done the x 2 minus x1 and the y2 minus y1. So you're going to have simply the square root of negative 5 squared plus 12 squared, which is going to give you the square root of 169, and the square root of 169 happens to be 13. So our magnitude, again denoted with a double bracket, is 13, and our component form of our vector is here, the little arrow brackets. And you'll be having to find those things on your worksheet and also in your textbook problems and on your tests. So that's really important. You have all this in your notes and you have these examples to look at. So pause and take note of all that. All right, we have quite a bit of notes. The final thing we're going to talk about tonight is vector operations. We have a whole other video tomorrow night where we'll continue vectors, but tonight we're going to stop at vector operations. I want to talk about that and introduce that tonight, and there's quite a bit of note-taking, so you're going to want to pause quite frequently and write this down. Vector operations, there's basically two types of operations. We have scalar multiplication, and then we have vector addition. In this particular textbook, our scalars will always be real numbers, but that is not always true. You want to pause and write all that down and make sure you have that in your notes because there's some additional notes in the video tonight that won't be on your note sheet tomorrow, and you're going to want to annotate and add those to your notes so that you have all that information. Okay, so pause, and then I'm going to go on so that we can keep moving. All right, geometrically. The product, and this is kind of interesting, you really try to understand this, that would be multiplication, of vector, which we represent with the letter V, and a scalar, which we'll represent by the letter K. Okay. Is the vector that is k times as long as the original vector v. So in other words, I like to call that a multiplier. In other words, if you're dealing with scalars, it's like you're multiplying things. And I know that's very simplistic and it's more complicated than that, but that's just a really quick and easy way to know that. If k, this is the part that's really important. If k, the scalar, is positive, then your vector will continue in the same direction. However, if k, is negative, so if the scalar is negative, you're multiplying by a negative number, then your vector will travel. And you know what? I'm going to leave it for you to find out. You either Google it or you can look it up in your book, but I want you to tell me in your own words what happens if the scalar is negative. You have a computer in front of you, just Google what happens when scalars are negative, what happens to your vectors, and write down, and I want you to fill in that blank. I'm going to look for that in your notes tomorrow. All right, I'm going to pause for a minute, let you write that down and look that up, and then write that in your notes, and then we're going to go on and finish up. Okay, well, I hope you found the answer to that question. I'll be really curious on how many of you did. Okay, next I want to talk about the sum, or we're adding vectors. You can also think of that if you may be adding negative vectors, so that would be okay too. Then you would think of that more as subtraction, but it's still all going to be under the umbrella of sum. So the sum of vectors, which would be an example, you would see vector u plus v, is formed by joining the initial point of the vector to the terminal point of the initial point of vector v to the terminal point of vector u. This is called parallelogram law, and we're going to see why next. I also often call it tail to head or head to tail, and you'll see why, and we'll talk about some resultant vectors. And you may have already discussed this in physics before. So let's take a look at the example. So I'm going to draw myself a little plane here. All right, we're going to have vector u up here, and this is the initial point, and then this would be my terminal point. And then I'm going to have vector v. Okay, sorry, that's vector u. I should have drawn them over here. So this is vector u, and here's vector v. I'm just going to draw another vector, and it's going to look something like this. Okay, so if I take vector u, and I draw it on my plane, and then I attach vector v to the terminal point of vector u. In other words, I'm going to start vector v right here, but remember it's got to go not only the same distance, but it's got to go the same direction. So vector v would travel off something like this, and that would be my vector v. My resultant vector is going to be from my initial, and resultant means of the sum of those two vectors. If I added those two vectors together, this would technically be u plus v. My resultant vector would start at the initial point of the first vector, and it would end at the terminal point of the second vector. So this would be my resultant. But notice, had I taken this in the same direction, had I taken vector u and gone over here, or I'm sorry, attached vector v to the terminal point, and I attached, so this would, I would have started with vector v, and then I would have taken vector u and attached it. I didn't draw a really good picture, but that will create a parallelogram, and that's why it's called parallel law. So this would be u. So this if I had taken v plus u. And since we're talking about addition, that would not matter which direction you started with first. So v plus u would have gotten me the same resultant, although you would have gotten there a little differently. All right. When you come to class tomorrow, I want you to pick up your worksheet on vectors, and then I want you to find a place on the worksheet to write the properties from page 451. There's a blue box in the middle of page 451, and I want you to find a blank area, or you may write it in your notebook, but I want you to write down all the properties as soon as you come to class tomorrow, even before the bell rings. I want you to write that down. And as I come around to give you credit for your notes, I will take a look to make sure you're writing that down, and I also want to see the answer that you Googled to find out. Okay, we're going to pause for a second, and then we're going to end with 3 examples from operations, and that should get us started on vectors tomorrow. Okay, we're going to end up with these 3 examples, and we'll be on our way, so let's go Bearcats. Here we go. So we're going to vector V, which is in the component form, and that's why you know it's a vector, the little arrow brackets, 2, negative 2, 5. Remember, those values came from 2 ordered pairs. And we have vector W, and vector W is represented by 3, 4. That's the component form of the vector. All right, the first thing we want to do is part A. We're going to do 3 different operations using these 2 vectors. We're first going to go 2 times V, or 2V. 2 is a scalar, just so you know. Remember, I told you it's like a multiplier. And so we're going to actually have 2 times, and then our component form 2, 5. When we do that, then all of a sudden, we're going to end up with component form negative 4, 10. Then we're going to have B. Part B, we're going to take vector W and subtract vector V. And we're just doing the operations now. All right, so we're going to take vector W. Vector W is component form 3, 4. And we're going to subtract component form negative 4, negative 2, my bad, 5. All of a sudden, remember what we're going to do is we're going to have 3 minus negative 2. 3 minus negative 2, which is plus a positive, and we'll have 4 minus 5. All of a sudden, then that gives us 3 plus 2, which is 5, and 4 minus 5 is negative 1. And so W minus V would be component form 5, negative 1. And finally, I'm going to move over here to the side so I have a little more room, and we'll do part C. And part C, we're going to have vector V plus 2 times W. And remember, 2 is like our scalar. And here's what's going to happen. Component form of V is negative 2, 5. Then we're going to add to that 2 times W, and W, of course, was 3, 4. So we keep our component form negative 2, 5 for V, and we're going to add to that, we're going to multiply, we're going to use our scalar as a multiplier, and we'll get 6, 8. And now we're going to add negative 2 plus 6, and we're going to have 5 plus 8. And all of a sudden now V plus 2W would be negative 2 and 5, or negative 2 and 6 would be 4, and 5 and 8 would be 13. And that would be your final answer. All right. Hope you have a good night. Don't forget to Google the question, and don't forget to come in tomorrow and copy down that box from page 451. Have a good evening. Night, Bearcats.